Are we?
We're good.
We're good? So this is the way we're going now, huh?
Where are you? That was not funny.
We can go tall and thin if it's easier for you to keep track of. Like
It's
I said,
okay.
You're in charge.
It'll be fine.
Okay.
It worked the first time. It worked the first time.
That's because it was doing it this
We
way.
were doing it that way, but Melanie can't see. You know, she's guessing every time I move. Okay.
Move my hair.
So we ended up with pyruvate kinase last time, right? And so we talked about this. So there is a figure in your book. In the old edition, it was 1513. Kyle, is it still 1513?
Yes. Yes.
Yes, a keeper of the great loose leaf book file. So, right, phosphoenolpyruvate, again, magnesium ion involved. ADP acting as nucleophile, and here we go, right? What's the magnesium ion doing here as part of the reaction? If we're relating this back to the principles that we learned about these reactions in organic chemistry. Yeah, it's acting as a Lewis acid, right? In organic chemistry, what did we normally use in this place?
Hydrogen.
A hydrogen ion. Right? So it's protonating this leaving group. Right? It's acting as a Lewis acid to stabilize the Lewis-based leaving group. So when that leaves in our nucleophilic acyl substitution, our product is the, in this case they're showing the deprotonated enol pyruvate form. Stabilized by the magnesium ion. And the tautomerism of that enol pyruvate to the ketone, ultimately protonating that, right, that carbanion that would form there, right, creates the pyruvate. And it's this tautomerization that ultimately provides the energy that makes this favorable and able to make ATP. Notice, this step of the reaction they're showing as an equilibrium reaction. It's only when you get the strongly favorable tautomerism that you pull this equilibrium through to make synthesis of ATP favorable. Okay? Does that help you see what we were talking about last time? And then we talked about the control of pyruvate kinase. Right? Pyruvate kinase as the exit of glycolysis is also controlled. Right? We said we talk about control at the entrance and we talk about control at the exit. So we were talking about fructose 1,6-bisphosphate being an activator. Why did that make sense?
Calls ahead to the pyruvate kinase.
Yeah. Calls ahead to the pyruvate kinase and says, you know, stuff coming, get ready. Feed forward inhibition by ATP. Right? If we already have ATP, we don't need to be sending a lot of stuff through glycolysis. Acetyl-CoA, also signaling that we have plenty of other sources of carbon to make ATP already going to the mitochondrion. If that's already going to the mitochondrion, we don't need then to continue bringing things through out of glycolysis. And we were on this one at the end of the hour. That is, the enzyme in liver is phosphorylated by a cyclic AMP-dependent mechanism. So that means what hormones are causing this? Evan? You got one, glucagon, epinephrine. So in response to either big hand right there.
I was
right?
thinking since you were asking, it wasn't those.
Don't overthink these. I can't always remember what I put on my slides. How many times have you seen me do that? Ask you something that's sitting there staring you right in the face. So, glucagon or epinephrine, does that make sense? Right? That glucagon or epinephrine would inhibit pyruvate kinase and therefore inhibit the exit from glycolysis in the liver. Well, glucagon and epinephrine, in general, what are they signaling the liver to do? Either low blood sugar or run away, right? In either case, what do we want the liver to do? Stop using glucose and start exporting glucose, right? So, right, all three of those should make sense, right? There shouldn't be anything surprising in those results. So, right, this is where we are now, right? We said we would take glyceraldehyde phosphate. We made 2 of them, right? 2 3-carbon phosphates from our 6-carbon bisphosphate. Now, we generated NADH, so that would be 2 of those. We generated ATP twice, that would be 2 there and 2 there. So our net gain right now is an NADH. That got us back to even ATP-wise. We gained 2 there. So all of glycolysis, for every mole of glucose that goes through, we only gain 2 moles of ATP. Seems kind of wasteful. What's the advantage? Why is glycolysis so central then? Yeah, pyruvate, I'm assuming this means this, what cycle? The citric acid cycle, yeah, this. So, yeah, right, the pyruvate can go into the citric acid cycle. And oxidation in the citric acid cycle, at least on a per carbon basis, is much more efficient. So it sets us up to send carbohydrate carbon into the citric acid cycle. But what's the other reason why glycolysis is so important? We can do it without oxygen. That's important. I wasn't going there, but that's important, right? At least nominally without oxygen. We've still got this reduced compound hanging out here that we have to deal with. What's the other thing, though? The other reason why we really need glycolysis. Glycolysis is just faster than anything else in releasing ATP for short-term needs. Right? Even though fatty acid oxidation is more efficient, in terms of the time it takes to generate that ATP, fatty acid oxidation is slower. So we can generate more ATP per second using glycolysis. And it's that efficiency which makes glycolysis so important to us. So in those moments, just after we realize the saber-toothed cat thinks we look like a meal, when we want to be able to get away quickly and we need to generate ATP, a lot of ATP in a short time frame, and we don't really care how efficient it is, that's where glycolysis is the most useful in terms of how quickly it can generate ATP for short-term needs. Does that make sense? Okay, but we do run into a small problem here that we need to address. Let me make sure this is where I want to go. It is where I want to go. Good. That is, where is this NADH being generated?
In the cytoplasm?
In the cytoplasm. Remember, the cytoplasm is a small space. There are a limited number of NAD molecules in that small space. And if you're going to generate a lot of ATP in a short time, then you've got to run a lot of stuff through here. And since you have a limited number of NAD molecules to start with, you're going to convert a large number of those to NADH, which means you're going to start running out of NAD, which means what happens to this step? it slows down, right? As your substrate concentration goes down, we know that it will slow down. The other problem is these NAD using enzymes are usually strongly product inhibited. So if we can't do something with the NADH, not only will the reaction slow down because we're running out of the starting substrate, NAD, they'll slow down even more because NADH is actively inhibited. Oh, there's my NAD. They'll slow down even more because NADH will start competing with NAD to bind and actively inhibit the enzyme. So this becomes the limiting factor in continuing glycolytic activity. Okay? So before we can really close the book on glycolysis, we have to figure out, if we're going to keep doing glycolysis, how do we recycle NADH to NAD so that we can keep going? Okay? So, we've got three ways of dealing with it, depending on where we are and what we are. Which one do you want to deal with first? Jordan, you get to choose.
So,
Door 1, door 2, or door 3? We're going to go, let's make a deal on
inhibits the
this.
enzyme that forms it. Kind of.
Yes.
Yes, okay.
Door number 3. Jordan chooses door number 3, alcoholic fermentation. Should we take a message from that? Okay, so alcoholic fermentation. Now, where does alcoholic fermentation go on? In what kinds of organisms? Well, one's obvious.
Us.
No.
Oh, wait, no.
Oh, come on. What do you need to make alcohol? Yeast, right? So little yeasty beasties do alcoholic fermentation, right? And the whole point of alcoholic fermentation is, in the absence of oxygen, taking that NADH and reoxidizing it to NAD so that that NAD can go back up here and keep glycolysis running. Right? That's what the yeast are trying to accomplish. Let's see. Is that where we go first? That's not where I went, but that's okay. We can go. Let's see where we go. So, if we're going to do alcoholic fermentation, we go this way. Anything that does alcoholic fermentation, you start with pyruvate, right? Where glycolysis ended. And you need an enzyme, pyruvate decarboxylase. Pyruvate decarboxylase, now they're missing a hydrogen ion coming in here. Pyruvate decarboxylase decarboxylates pyruvate. That is, it takes off the carboxyl group, leaving acetaldehyde. Acetaldehyde then can be reduced, right? There is everyone's favorite enzyme, alcohol dehydrogenase, working in yeast, uses NADH as the reductant to reduce the aldehyde to a primary alcohol, and you make ethanol. Does that make sense? Now, what kinds of organisms can do this? We said yeast can do it. Other bacteria can do it. Actually, most industrially produced natural ethanol is made using bacteria. Who else can do it? There's an interesting story of, all right, in general, most higher animals can't do this. Right? They don't have the pyruvate decarboxylase. Now there's one interesting exception to that. This is one of those things, I stumbled across this paper. I used to like doing offbeat seminars. You know, everybody else would do their their graduate school seminars, class seminars on whatever their research was. I liked finding offbeat